And share my screen. All right, and then something I want to show some of you. Everybody can hear me, I assume?
Yeah.
Okay. So something I want to show you here is this was a site one of my other students brought up that I've been pushing students to more recently for like practicing coding. There's this site called codewars.com. So when you go to codewars.com and you sign up, you can, so for instance, and here we're using Java, so you can change your language that you want to practice. So I'm just going to kind of go through the
Are
most.
you sure it's a Cold War?
Codewars.com. You can see the URL
Okay.
on my screen. So I'm going to make sure I choose Java here. Then hit save. Now I should have Java in my selections. Okay, so I'll choose Java as my language. And then I'm going to go ahead and I'm going to click up over here on the left-hand side. There's things called like kata. I haven't messed with them too much, but I think katas are like practice problems. So I'm going to click on kata here. And you have the difficulty level over here. So an 8 KU is like the easiest. A 1 KU is harder. So let's just say you're a beginning programmer and you want to just start off with an easy problem. Presumably, hopefully I can do the easy problem. All right. So here they have 303 easy kata problems solved. So here's one, this array plus array. Let's just look at this one real quick. So I'll click on that. So let's see, I'm new to coding. And now I want to get the sum of two arrays, actually the sum of all their elements. Okay, so some people, I guess somebody just created this problem. Some of them are more formally written than that, but so you have a couple of arrays. Each one contains integers. The output should be a number. So we'll hit train on this one. So you see over here, it gives us some code, array plus array. It takes in two arrays, and we want to sum up all of the values that are in there. So I'll come in here, and we're going to go through. I'll just say int sum is equal to 0, and I'll write a loop that goes through all of array 1. So for int I is equal to 0, I is less than arr1 dot length I plus plus. Kind of indented funny, whatever. Then I'll say sum plus equals arr1 at bucket I. Then I'll do the same exact thing here for arr2. Sum plus equals arr2 at bucket I. And then I'll return the sum. Okay, so this is a function that takes in two arrays. I create a variable to hold my sum. I go through every element of the first array, adding each of those elements to my sum. Then I go through every element of the second array, adding each of those elements to my sum, and ultimately return the final sum. I can go down here and click test, and that'll run my the test scripts on it or whatever. So it says, you've passed all the tests, blah, blah, blah. Then I can go ahead and hit attempt, which I guess runs it on more tests. And it says I passed. So I've completed this solution. So whether you thought that was an easy problem or a hard problem, it doesn't really matter. Just this is a nice site to go to kind of practice programming drills, starting from, again, when I go back to just the kata section. If you want to go to very easy problems first and then challenge yourself a little bit more, and like again, if I go back to the easy problem, so here's the array plus array, multiply, returning strings. Like some of them are more formally fact, you might be able to, here, I'm going to say sort by popularity, maybe. Maybe it'll give me a better selection. Yeah, here's one called multiply. Let's see if that's worded better. No, that one's not worded better. Create a function that takes an integer as an argument and returns even for even numbers and odd for odd numbers. All right, so, you know, again, an easy problem, but something that is, you know, more, you know, formally written. So in any case, this just gives you, so here, this is actually, this is a good use if you haven't seen one in a while for an inline if statement. Returns a string, so I'll return number mod 2 equal to 0, even, odd, like that. Kind of a good use for a what are you upset about? Oh, it's a question mark, not a that. So if you haven't seen an inline if statement ever or for a while, this is the Boolean expression. So this will boil down to true or false. If it's true, this whole line boils down to even, otherwise it boils down to odd. So this solves that problem, but this one is written a little bit more formally. So in any case, this is a nice place to come to kind of give yourself practice problems that maybe are sometimes hard to come up with on your own. So for those of you who kind of expressed some concern that you know, don't have a lot of confidence in your programming skills, or it's been a while since you programmed and you're rusty, coming here and kind of treating this like your video game for an hour or two some afternoon might be a good way of you know, brushing up on some of your skills, something like that. All right, so this isn't an assignment or anything. This is just a tool that I wanted to introduce to you in case it was beneficial to you. I'm going to mess around with it. I think it's, I don't know, it seems to be pretty interesting at the very least. I mean, every now and then I might run across some questions from this and I might use in some of my programming classes for exams or something. So, so any questions about this? I just wanted to introduce it to everybody.
I have a question.
Sure.
Does it give the answers, like if we run into some problems?
Well, it
Like
like, are you saying, is there a way to get the answers? Like,
yeah.
There is, because like there's responses to these. Like I said, I haven't used this tons. I already hit submit, didn't I? Let me go back to the actual problem. Yeah, so here's like some other people's responses. Oh, this guy stole my one-liner. So did he? Yeah, here's the more normal one, you know. So if the number is even, return even, else return odd. So you can see different people's solutions in there, you know. So you should probably refrain from looking at those, but you can get solutions. You can also ask questions. You know, some of them are pretty popular where, you know, there's some stuff. Now this other thing over here, this Kumite, I haven't messed with it yet, but apparently it's like supposed to be the competition side of things. So I have no idea how it works yet, but I'm thinking this is more like you play against other people. So you know, it's like a back and forth thing. Let's see. Kumite is the practice of taking techniques learned from kata and applying them through the art of freestyle sparring. You can create a new Kumite, providing some initial code and optionally some test cases. From there, other warriors can spar with you by enhancing, refactoring, or translating your code. There is no limit to how many warriors you can spar with. A great use for Kumite is to begin an idea for a kata as one, and you can collaborate with other code warriors until you have it right. So I guess the idea is if you have a problem you want to kind of solve, you can put it out there as a Kumite and let people help you evolve it to a better question or something. But just from using this as a tool, it looks like Kata is the place where you go to just practice. And there's lots of languages in here. I was pretty impressed. But it's in any case, something worthwhile looking at. If you don't have a lot of confidence in your skills, this is a place you can go to just work on it. And you could pick from like a bunch of languages. So for here, you probably want to use Java, but Python's in there. Like a lot of languages, surprisingly, are in there. Okay, so let's go back to our stuff. So I'll be looking at the assignments today. Everybody should have created a hello world and put it up on GitHub. So I'm going to assume starting right now that everybody's able to submit homework via GitHub. So today we're going to continue to talk about some language stuff. Let's see where we left off last time. Okay. Yeah, so last time we were talking about the how humans solve problems, the nature of the CPU. Ultimately, how do our modern programming languages get us there? So we have to develop a syntax that we like, and we're going to kind of invent that ourselves. And here we're going to decide on, when we tell a computer what to do, what words will we use. So we'll probably do something based off of like the C programming language loosely, but still have our own words, so it still feels like we're the language creators and creating the interpreter behind the scenes. We then have to parse those into something else, and we're going to be talking about parsing today. Then we need to process the parse syntax using some logic, so that actually is performing the actions, and then ultimately we get that into a form the computer can understand. So if we're going to think about this in maybe a real life scenario based on some stuff, let's just think about how Java works. So we can write some Java syntax. Well, actually, let me just do it this way. So we can write some Java syntax. All right. And then we run that Java syntax through the Java compiler. And the Java compiler will parse our syntax and ultimately convert it into something called Java bytecode. Java bytecode then will be executed on the Java virtual machine. The Java virtual machine interprets Java bytecode into call it low-level native code for CPU, and then it ultimately runs on the CPU. So that's the full life cycle of a Java program. Okay, we write our Java code, we then compile it, it then turns into Java bytecode, which the Java virtual machine knows how to run. When it runs it, what is it actually doing? It's converting that into low-level native code for the CPU we're on. So if we're on a Windows-based machine running Intel-based processors, and let me kind of give you the idea behind that. No, that's actually not going to be that important for us right here. Okay, so so this program is built for running on the Java virtual machine. The Java virtual machine is a program that was built for running on Mac for Intel processors or Windows for Intel processors, whatever. So ultimately it's going to be getting converted or mapped over to those instructions that'll then run directly on the CPU. All right, that's the life cycle of our running Java program. Now, we didn't write this. We didn't write the compiler. None of these things were we in control of. Those were other tools that were built for us. Okay, all we did is wrote the Java syntax. So now, what are we going to create in here? Well, we're going to, how is ours going to differ? So we're going to have, we talked last time how compilers are complex. We're going to be writing an interpreter. So we're going to maybe call this guy R syntax. Will run through a parser, which then runs through an interpreter that ultimately translates to low-level native code for the CPU, which then ultimately runs on the CPU. So we're going to invent what our syntax should look like. Then we're going to write this parser and we're going to write this interpreter. So these are the pieces that we're actually going to create in here. We're going to rely on, since we're using Java in here as our programming language, we're going to be using Java syntax for representing this parser and this interpreter. So all this other stuff up here is already done for us. That already exists in the Java ecosystem. So we don't have to invent a compiler or anything like that. We're effectively going to write a computer program that knows how to read in our syntax, parse it into something else. We'll talk about parsing today. And then ultimately interpret it, make it do what it was meant to do, something like that. Okay, so what we're going to start off with today is kind of inventing our language a little bit, and then we'll start working with some simple parsing steps, getting us to a point where then your homework assignment will be to write a little bit more of the parsing stuff. All right, so what I'm going to do is I'm actually going to start a new repository. So I'll come down here to Git desktop. I will create a new repository. And we're going to call this guy CSC549 underscore let's call this guy fall 2020 underscore interpreter. All right, because this is going to be the project we're going to be building on top of. All right, so I'll go ahead and create that repository. That created a folder for me in my downloads folder, in my case. So now I'll go over to Eclipse. I'll close all this stuff. I'm going to create a new Java project. Project name will be CSC549 fall 2020 interpreter. But instead of the default location, I want to browse to the folder I just built in my downloads, CSC549. So here's my new repository I just created. So I'll say open that. So that's where I'm going to store my project. I'll go ahead and hit finish. Remember, don't create this module. So I'll say don't create. And now I have my project here. All right, so I'll go ahead and expand that. We'll go ahead and just turn it into a working hello world program just so we know that it's working initially. I almost always do that. I almost always create a class called driver. If you've already written main methods a bunch of times, you can also hit this little checkbox and it'll actually create that for you. But if you aren't already comfortable writing that, I would suggest you practice writing public static void main string array args on your own until you get good at that. So one skill you want to have as a software engineer is the ability to kind of write the core template program in a lot of different languages. That type of skill set. All right, but it's in there for you. So here, this is going to automatically give us. I don't like how they do their curly braces. So I'll just do my system.out.println hello world, and I should be able to hit play. And there's my hello world thing there. Just to test our connection with GitHub now, I'll go ahead and I'll push this to GitHub. We'll obviously be pushing some updates, but just to review the whole GitHub thing, this was your homework assignment. So up to this point, I've basically redone your homework assignment. So we'll just complete that. So I come back over here to Git desktop. It notices that here I got to bring up, which is the repository. Okay, this guy right here. And I'll go ahead and just say initial commit or commit to main. All right, so this now made my local repository up to date. So I'll go ahead and click publish repository. This is me putting it up on GitHub. I'm going to call it the same thing. I'll make sure I uncheck this so it's not private. That way I can, you guys will be able to see it. And then I'll say publish repository. All right, so now it is up there on GitHub for other people to see. All right, so that's kind of my working ecosystem here. I can now work on my project locally on my computer, then I can commit changes locally, and then I can push changes to the cloud. So that allows me to work on it on different computers if I want, or whatever. Okay, so let's start with doing some string manipulation stuff. Well, let's actually talk about what is a parser. Let's go that route first. Okay, so a parser reads in some text and converts it into a usable format. Something along those lines. All right, now we're going to start this off with just some kind of simple exercises, and I assume all of you have a computer in front of you, so we'll do some interactive stuff today. We'll be doing, we'll do this throughout, I guess, but I'm going to create kind of some puzzle stuff that won't feel like it's language stuff at first, but it actually is language stuff. You'll see what I mean here in a few minutes, but let's say, for example, we have, in fact, here, this was actually something off of Code Wars I just happened to see this morning. Let's say that we have a string that we're going to read in. So this might be like the syntax for a language that says a elephant lives in the zoo, something like that. So let's say we have that string. And let's say we have the rule that every string that's in here that has at least 5 characters in it has to be reversed. So we want our actual output here to be A B L I correction. So we want to parse this string and turn it into this string where certain components of it have been modified, something like that. All right, so that's kind of the concept of parsing a string. So if we read in a string like this, we want to split this guy up on something. So for this example, we'll assume that we just have one space separating the various tokens. Even though we see these as words, I'm going to start using some language terms. So each one of these is a token in this string. All right, so I'm going to read in a string that has these tokens in it, and I'll go ahead and actually just steal this string. You have a question? I'm going to take that as a no. There's somebody unmuted. All right, so I'll have this string in my program. And my goal is to get an answer. I want to write a function that turns that string into this string. Write a function that takes a string and replaces all words, or I'll say tokens, that are at least 5 characters long with the reverse of that token. So if this was the input, becomes this. This would be my output. Okay, does that make sense what we're trying to accomplish here in a little baby parser? So I'll start writing this function here. So I'll go ahead and we're going to make this guy public static. I'm going to have it return a string. And we're just going to call this guy parse. And he'll take a string s as a parameter. Okay. And ultimately, we need to return an answer down here. So what I'll do here is I'll go ahead and say system.out.println s. Then I'll say string answer is equal to driver.parse of s. And then I'll say system.out.println answer. And our hope would be that answer prints out this string in this case. All right, so what we want to do is we want to write the code here that converts this string into the equivalent string with the right tokens reversed. So I'll give you a starting point for this, and then I'll give you a couple minutes to kind of try to take a stab at this on your own. And this hopefully will give you kind of an idea of where your current skill set is. So usually I'll give you some starting code, like the homework for Monday is going to have, I'm going to do a bunch of the stuff in here in class today, and then you'll have to do more things like what I did. So the same kinds of things, but just more of them, something like that. All right, so I'm going to go ahead and I want to split this string up into its parts. So I'm going to create a string array called parts. And this will be s dot split. I'm going to split on spaces. All right. So right now, parts is going to have, so if I were to say something like system.out.println parts dot length, this should be 1, 2, 3, 4, 5, 6. Okay, there's 6 parts to the 6 tokens. So I'll see a 6 here. And then just so it runs, I'll go ahead and return the empty string. Or actually, I'll just say I'll return woot. So right now, my function always returns a woot from this guy. All right, so I define a string up here. I print that string out. So a elephant lives in the zoo. Then I get my answer by calling driver.parse. That's this guy. I pass my whole string in here. I split that string on spaces. I should now see here, it'll print out a 6. 1, 2, 3, 4, 5, 6. I have an array of 6 individual strings. If I were then to print out, show me string at bucket 1, that would be elephant. So I can say system.out.println parts at bucket 1, for example. And that'll give me the elephant. All right, so there's my full string, there's my 6, there's the bucket 1 is elephant, and there's what I returned. All right, so the punchline here is that I just showed you the evidence that this line right here will break this string up into its individual pieces, separating it by spaces. And just to connect this to languages a little bit, consider if we're writing Java code, every quote line of our program is separated by a semicolon. Generally speaking, I think that's fair enough to say now. So in this case, we're saying that the tokens of our language are separated by spaces. Okay, in our little example here, we can assume there's only ever one space in between there. So we'll have our the correct number of tokens. All right, so we want to now finish writing this code, this parse, so that it goes through every single one of these strings and keeps the ones that are less than 5 characters long and replaces the ones that are at least 5 characters long with the reverse version of itself. Now, if you want to have You know, a lot of folks, they'll sit there and think, well, is there already a built-in reverse function in Java? I think there is inside of a class called string buffer, but I wouldn't rely on that. I would just go ahead and write my own little reverse. Static string reverse. This guy could take a string as a parameter. Let's create a string called answer for int I is equal to 0, I is less than s dot length, I plus plus. We'll say answer is equal to s dot charat I concatenated with answer. So we'll build it in reverse, and then we'll return our answer. So if you want to see that here, I can say here. Driver dot reverse. Here, we'll reverse woot. That should give us, I don't know, how do you pronounce it? TOOW. So there's the reverse of woot. So now we have a tool here that allows us to reverse a string that we only need to use when we actually want to reverse strings. Okay. So take a couple minutes and try to finish writing this parse so that it splits the string and outputs a new string. So returns a new string that has every element of parts that has at least 5 characters in it reversed. So for example, if the input looked like this, if that was S, we should return this. Make sense what I'm asking you to do? All right, so take about 5 minutes and 5 minutes-ish and try to do that on your own machine. And then we'll come back and work on a solution to it here in a second. I guess while you're doing that, I'll go grab a drink. So. And here I'll go ahead and I'll push this to my GitHub repository as well, in case you want to reference from mine. I just put the link to mine on Slack. So if you want to be able to see the entire program on one screen, as opposed to having to look at it through, you know, me having to scroll and stuff here, you can use the rest of mine as a reference right now. All right, I'll be right back.
Professor,
Yep.
I have a question.
Okay.
I do not understand the coding. What's going on here?
Okay, well, that's not really a question.
It was really fast for me.
Well, so you should be able to walk through it now. I mean, if you look at main, this is what main says to do, right? You know, create a variable, print it out, call this other function, driver.parse, which is what we're writing down here. You know, so if these are things you can't follow yet, then that's fine. But these are things you're going to have to figure out how to do on your own, because I'm not going to teach, you know, beginning programming in the class, but hopefully you can follow along when you see our solution to do it. Does that make some sense?
So what is the driver?
This is the name of a class in Java. So this is beginning programming concepts.
And dot parse is the function name?
Yeah, that's a function name that we wrote down here. So we're writing it here. We're calling it up here.
And then driver dot reverse boot is.
That's this other function I wrote called reverse. So I wrote a function here, and I'm calling that function here.
And the boot is the.
Just that's my input. This guy expects me to pass it a string. I'm passing it a string right here.
So what's supposed to be output?
Right here.
Okay, yeah, okay, yeah.
Okay, so let's go and let's take a look at this. All right, so I'm supposed to, and this is what told us what to do here. So I'm going to go through every one of these strings that are inside of parts, and I'm going to build a new string, which is the original strings, but with any of them that has at least 5 characters in it, replaced with the reverse of itself. I'm going to have a new string. We'll call this guy answer maybe. It'll be the empty string. I'll write a for loop that's going to go through every element of parts. So for int I is equal to 0, I is less than parts.length, I plus plus. And then in here, we're going to ask a question. If the current thing we're looking at, if parts at bucket I, that's the current string from a collection of strings, if that guy has a length that is at least equal to 5, I need to split it. Okay. So what I'm actually going to do here is I'm actually going to create a string called temp here. I'm going to set temp equal to the current part. And then I'll ask the question, if temp.length is greater than or equal to 5, then I'm going to overwrite temp with driver.reverse of temp. All right. So what does this code here do? This says, look, I'm going to temporarily hold my part inside a variable called temp. And if that variable currently holds something that's at least 5 characters long, I'm going to overwrite it with the reverse of it. So one way or another, when I get past this curly brace here, when I get to line 39, temp holds the correct string for me to use. It's either been reversed or not reversed. It's been reversed if the string was at least 5 characters long, or it's been not reversed. I haven't touched it if it's less than 5 characters long. So what do I want to do with it? I want to tack it on to my answer. Now, I could always just say answer is equal to the a space followed by a I'll concatenate onto it temp like that. And at the very end, that will give me a situation where answer technically has 1 extra space at the very beginning of it. You know, if I passed in a elephant lives in the zoo, this will give the output would be space a then elephant in reverse, then lives in reverse in the zoo, because I'm always putting this extra space in the front. So I could either conditionally put the extra space in the front, or I could return answer.trim, which will take the extra spaces off the front and the end, not in the middle. So trim just, cuts off any white space at the beginning or ending of a string. Either way, not a big deal for this thing. The real magic is what we're doing in here. So in here, we're going through every one of our strings, asking, is the current string I'm looking at have at least 5 characters in it? If it does, reverse it. Otherwise, just use what's already there. All right, so we'll go ahead and
Why the string is empty?
The string wouldn't be empty in this example. In this example, I'm assuming you're giving it reasonable stuff. This is just a little sample parser thing. We're not error checking whether or not our stupid example is doing it. But in our example here, you would never have an empty string because you're splitting on spaces. You have all of the individual strings between those spaces. So you have an A or an elephant or a lives or an in the zoo. Make sense?
But I mean the string answer equals to double quote.
This puts a space there. This is double quote, space, double quote.
In the above, underneath the s dot split.
Where are we talking about here?
So yeah.
Oh, this just starts it off as the empty string. I'm giving it this is like a string that equals nothing that I can build on top of. So these are things, once you see it work, you can walk back through it line by line and kind of see how it's happening. But I'll go ahead and show you the result here. So now this should have our correct input and output. Oh, hold on. Answer is equal to answer concatenated with that. I need to build up my answer, not just overwrite it each time. So there's my A, elephant in reverse, lives in reverse in the zoo. So there's the code that took in this input, parsed it, did something with it, producing, in this case, a new output. Typically, the output in our programming language would be, the result of our code executing. In this case, this is the output of our parser. So if I were to describe this right now, we have a parser that reads in a string, manipulates that string in some way, and spits out a new string. That's what our stupid parser is doing right now. Okay? And the code that accomplished that was this stuff right here. Taking a string, split that string into its parts based on spaces, build up a new string. How? Go through all the parts you have, and any of those parts that has a length greater than 5, make it the reverse of itself. Build up your answer string each time through. Ultimately, I returned the trimmed version of my answer. That's the answer without any extra spaces at the beginning or end of it. And that gave us this. Okay, so this is an example of a simple parser. Okay, not that this parser makes any sense. We haven't put any logic to this as to, well, why were we overly interested in replacing all 5-letter words or longer with the reverse of themselves? It didn't matter why. That was the job. Somebody paid us and hired us to do that job, and that's what we did. Okay, so for most of you in here, just to give you an idea for programming kind of background, this is the kind of code that you should be comfortable with. So if you know other languages and you need to kind of figure out Java's version of those things, that's fine. If this is all very new to you, that's okay. Just understand that that's going to be your responsibility to go out and look at things like codeacademy.com or which might be a good starting point if you feel like you have no programming background. I also have videos from my undergraduate programming classes that you can watch, but obviously each one of those is like an hour lecture. So, you know, you wouldn't be able to get through that as quickly. Code Academy is going to be more drill based. But in any case, that would be your responsibility for kind of picking up the slack there. Okay. All right. So that's an example of a, let's call it a simple parser. All right. So now let's make this more practical for us. So I come back in here. So this was our simple parser. We want to come up with a syntax for our language. Now, last time we talked about that. How do human beings solve problems? Memory, asking questions, and repetition. And we decided that 100% of programming languages have facilities for those three things. They have a facility for memory, a facility for asking questions, a facility for repetition. Okay, they all know how to do these kinds of things. So if we're creating our own programming language here, that means that we need our language to support these things and then some other things that maybe helps us make life a little easier on top of these things. So with that in mind, if we go back into Java and we think about, okay, if I'm in Java and I want to remember something, isn't that what this first line is doing? This is creating a variable named S and storing something in it. It is remembering. Hey. Okay, so it's remembering something. So forget about any of this other stuff here. You can comment them out for a second. This is an example of the programming language Java remembering something. Okay? So this is how Java pulls it off. It says, oh, well, you have a type. So int I is equal to 5, for example. So I'm creating a variable named I. I'm storing in there a 5. Okay? Now, if you're in Python, another kind of program, geez, I'm going to keep sneezing here. Let's get a drink.
That's it.
So if you're in a language like Python, you would just say I is equal to 5. Why is that? Let's just create a couple of slides here that talk about the differences in these languages. So programming languages come in different flavors. We have interpreted versus compiled. We're going to be writing an interpreted language in here because we don't want to have to invent the thing that takes, we talked last time, we had the thumb moving around, wiggling, right? We don't want to have to invent the thing that breaks down our human version of stuff into all those little tiny steps. We're going to leverage the existence of the Java compiler in here to do that. We're going to build an interpreter on top of that translates our code into Java logic, let's say something like that. But programming languages are either interpreted or compiled. They're either loosely typed versus strongly typed. And Java is a good example of this. Java versus Python is a good example of this. Java, which is a compiled language, also happens to be a strongly typed language. In Java, when we define a variable like this, when we're creating memory, so this is related to that first thing that all programming languages know how to do. They all know how to use memory, remember something. So in Java, when I create a variable to remember something, I also have to specify what kind of value that variable is built to hold. Okay, so in Java, Java is a strongly typed language. I built S to hold a string. I built I to hold an int, for example. If I was in Python, I can say s is equal to hello. I can say I is equal to 5. And then I can say s is equal to 3. Python allows that because Python creates variables in a loosely typed way. When I create a variable in Python, so a variable is a name value pair. That's what, in fact, I want to put that, I often use that phrase. I want to put that in here. These are name value pairs. It's a name associated with a value. That's what a variable is. Okay, so in Java, when I create a name value pair, like s is equal to the string, an elephant lives in the zoo, I also have to associate the type of value this variable is built to hold. Java would not let me say s is equal to 3 down here. If I hover over that 3, it's going to say, hey, s is built to hold a string. You're trying to put a numeric literal in there. Type mismatch, cannot convert from int to string. Because I specifically built this variable to hold this kind of value. And I was fine when I originally built it. But later on, I tried to store a different kind of value in it, and I was not happy about that. If instead I tried to put the string 3 in there, now it's cool again. Because it's saying, well, you built me to hold a string. I used to hold this string. Now you have varied my value to hold this string. It's a new string. Okay, so these are strongly typed languages where you give it a type when you define the variable, and then you're stuck with that type for the rest of the time. Okay, in a loosely typed language like Python, and a lot of, actually, most of the programming languages out there are loosely typed because most of them are interpreted. If we go back to our slides here, we look at this guy down here, these two bullet points have a lot in common with each other. Make sure it's not coming out of our class. Okay. These two bullet points have a lot in common with each other. An interpreted language tends to be loosely typed. A compiled language tends to be strongly typed. Just make sure there's not something important that's popping up here. All right, so most interpreted languages also happen to be loosely typed. That's kind of the nature of how interpreters work. It lends themselves to be loosely typed, where most compiled languages are strongly typed languages, because at the end of the day, a compiled language needs to reserve hardware registers and things like that at the CPU level. So if you're storing something that is of type int, it's going to specifically need to know that you're dealing with 32-bit values. Or if it's dealing with something that's of type string, it knows it's going to be dealing with a memory address that might be 32 or 64 bits, depending on the kind of operating system you're on, something like that. But the punchline is that compiled languages have a harder job to do, but also then have the ability to make those more efficient calls. Because if I just go right down the line here, I could call this relatively slow versus relatively fast. So an interpreted language tends to be loosely typed, which also makes it relatively slow. A compiled language tends to be strongly typed, which also makes it relatively fast. So these three things all have a lot in common with each other, but I say relatively slow and relatively fast here because computers are really fast. So all of our languages will feel fast enough, right? Python's a very popular language today, and it's an interpreted, relatively slow language. Okay, but because our computers are really fast, an interpreter like the Python interpreter allows us to create a syntax that maybe is easier to learn or something like that. I've heard some people refer to it as that. I don't know if I agree with that, but whatever. Let's assume that's the case, that interpreted languages are maybe a little bit easier to pick up because there's a little bit less structure to them. where Java being a compiled language, you have to kind of learn that initial structure of how the program is put together. And that's all fine and good, but at the end of the day, they're both programming languages. They both take in a syntax, they parse that syntax into tokens. Those tokens are then interpreted into logic, and ultimately a problem is solved. That's what all of them do. All right. The difference is that if we're operating at an interpreted level, we don't necessarily have to worry about how big of a footprint our data type is holding under the hood. We don't have, if our language is going to support strings, let's say the language we're going to invent it here, if it's going to support strings, we don't have to invent how the computer holds a string. Java already knows how to hold strings. So we're going to implement our string type on top of Java's string type. If we want ours to work a little differently, that's okay. We could do that. Okay, we can have our string work, always be uppercase or something like that. We can have it work differently. But it's still going to be built in terms of Java's string type as opposed to in terms of our computer's hardware. All right, so when you look around and see a programming languages today, for every one compiled language, you probably get another 50 or 60 interpreted language. You know, we talked about this last time when we were talking about the history of our programming languages and how we really have 5 or 6 compiled languages since the late 1960s. And you have, 5 or 6 interpreted languages that have come out probably since the beginning of class today. Something like that, because they're a dime a dozen. People create interpreted languages all the time. Sometimes it's just to make something that they're already doing easier for them. Well, just leave it at that for right now. All right, so we're going to choose to write an interpreted language because we want to focus on language constructs, not on how the computer works under the hood. So we're going to take the easier route here. We're going to choose to use loosely typed, not so much that you can't write strongly typed inside of a interpreted language, but we only have 8 weeks, so why make things more complex than they have to be? And we're going to be okay with our language being relatively slow because we won't notice. All right, so these 3 things, these all relate to each other. It's relatively slow, relatively fast thing. That was just, something I threw in there to kind of tell you the difference here. Programming languages then also are functional versus procedural versus object-oriented. All right, and we're going to hopefully have time to get to object-oriented stuff in our language. Usually we want to think about functional languages as almost being thrown out the window. They're just very different. So at the end of the day, we're talking about procedural versus object-oriented. And the idea here would be is a lot of time, well, the easiest way to explain that just at the high level right now, before we get to a real example at some point where I can show it, is we can think of all programming languages as being procedural, but some procedural languages happen to leverage objects to solve the problem. Now, remember, the job of a programming language is to allow a human being to solve problems in a way that's similar to how they already solve problems in real life. In real life, we work with objects. A little bit ago, I left to go get a soda. I came back with a can of soda. This is an object that has a little tab thing on top of it. When I pull the tab up, when I interface with the public interact with the public interfaces of this can, I was able to unlock it and get the soda that's inside of it out. I was able to use this object. Similarly, I have my phone here. I have let's see, there's a TV remote here. So if I want to turn the TV on, I use my TV remote, which has a whole bunch of functions on it, and that's an object. The remote is an object that I use. So in real life, we think about the things around us in terms of actual objects, knowing full well that those objects have a lot of magic inside them. We know that this TV remote has circuitry and stuff like that, where each button means something different, and I can control this device across the room with it. All right, and that's going to be a different kind of magic inside of it than is in the soda can, which is relatively dumb, right? I have one point of entry and it's made of metal, but it holds some liquid. That's its job. Okay, it's not a can of soda costs a lot less than the TV that the remote's controlling, but it still is an object. It's still solving a purpose, right? Something like that. That's how we think about the world around us and how we solve problems in the world around us today. With that being said, when we go back to the earlier computer programs, which would have been procedural programs, and you could think of procedural as kind of monolithic, just one line after another, do this, then this, then this, then this. We really didn't need to use objects to solve the very early problems in computers because we didn't perceive the power. Well, computers weren't as powerful as they are today anyways, and we weren't leveraging them as much as we do today. So we didn't really see the weakness in having to talk to the computer more like a computer. The computer feels less alien to us now than it did back in the early days. Right? Even when you're trying to learn a new technology today, like as a web programmer. So when you take the CSC560 class, the RESTful API class, we use Node.js and Angular and MongoDB to create, like a web application, RESTful API thing. Well, if you had grown up with computers through the 70s and the 80s and the 90s, certainly 70s and 80s, when before you had graphical user interfaces, you would be very accustomed to using a command line. So for instance, here's the terminal. You would be accustomed with your entire screen looking like this, not having a mouse or a keyboard or anything like that. This is commonplace to you, okay? But most of you didn't grow up during that time. Most of you grew up in the thousands or the late 90s, something like that, where you've always had a user interface. And maybe some of you are familiar with DOS, so the terminal and the Mac OS, but it's not something you grew up with. So one issue we run into with learning web-based languages today, like in that 560 class, is we have to go back and teach you how to interact with a command line interface, a CLI. This is a command line interface right here, because a lot of times you're working with command line tools like this, where we, as normal technology users, we haven't necessarily been trained to do that. Even with Java, when I started writing Java, I'd write it out here at the command line and compile it from the command line and run it from the command line. Now what do? I hit a play button, right? I just hit that guy and my program runs. So this is different than it used to be. And that's something we want to consider when we write our languages or consider languages. So in this case, in the early programming, early problems programmers solved with a programming language, they didn't see a need for objects because they were already used to talking to a computer kind of like a robot. They viewed computers as being more alien than they are today, where now computers are becoming more and more human, right? Most of you can sit there and you can talk to your phone, whether it's Siri or Google Assistant or whatever it is, where, the technology is becoming more and more human so that we don't have to act so weird when we're interfacing with it, which is great. That's a great convenience for human beings, but it also is an inconvenience for technologists like us training to be computer scientists, because we haven't been exposed to the awkwardness of computers as often as you would have been a long time ago, right? Grandma can use a computer today. Back in the 1970s, grandma probably wasn't using a computer. Grandma didn't know how to use a soldering iron type thing. So, we just have to kind of understand that because of the way things have changed, even modern day computer science students have a different appreciation for some of this stuff than they would have had if you were a computer science student in the early 90s, where you would have viewed the world of writing software significantly differently. Writing in the 80s, you would have written your programs using punch cards and brought out your whole program would just been a stack of cards you brought over to this thing to run through a system. So, the world has changed. So we still want to have an appreciation for some of these things, but, obviously we're probably in 8 weeks not going to write some sort of killer programming language that's going to be the next evolution of stuff. So actually what we'll be doing is working with some older concepts, trying to maybe appreciate how things got to where they are today from maybe where they were in the 80s or something like that. Okay, but clearly the way we solve problems in the world today is through objects. We will try to give ourselves an ability for representing objects in our language, but it won't be the first thing we do. Initially, we're going to say, hey, I want to remember stuff. Hey, I want to ask some questions. Hey, I want to do some repetition. You know, the basic constructs that allow us to meet this requirement that 100% of programming languages have facilities for memory, asking questions, and repetition. All right. So functional versus procedural versus object-oriented. Let's go general purpose versus domain specific. So general purpose would be like the languages you've heard of: Python, Java, C++, C#, C. These are languages that allow you to solve any kind of problem that a computer programming language can solve, as opposed to domain specific languages might be like your dishwasher might have a computer embedded in it and has a small language that allows you to interface with the 3 or 4 modes that the dishwasher knows how to go into, something like that. A lot of those languages are called embedded systems. A lot of them are written in C. So they're still written in a modern programming language. It's just a subset of that for you to interface with a device. Let's see, what else can I say about languages in general? Precompiled, loosely typed. Is that it? Let's go with that for now. All right, so these are the different categories that languages fall into. What we're going to be looking at in here is a interpreted, loosely typed, object-oriented eventually, but at least procedurally at first, general purpose programming language. And we're going to be building that on top of, so that's the language we're going to be building. We're going to be building that on top of a compiled, strongly typed, object-oriented, general purpose programming language. Okay, so that's the guy that's going to do the conversion for us so that we don't have to invent a compiler. All right, so with that being said, let's talk about variables. I mentioned earlier, variables are name value pairs. So if I told you to remember that A is equal to 5 and C is equal to 7 and B is equal to 14. Okay, I tell you to remember those things. And then I ask you, oh, what's the value of C? The value of C would be 7, right? You looked it up somewhere. So I told you to remember it. You can memorize that in your head for probably a couple of values. Otherwise, you write it down somewhere. It's stored in your brain somehow, wherever. You put this collection of name value pairs somewhere in your mentality, right? So A is equal to 5, you store somewhere. C is equal to 7, you store somewhere. B is equal to 14, you store somewhere. Now, later on, I come and ask you, oh, what's the value of B? You look it up inside your brain and you come back and say, oh, B's current value is 14. That makes sense? All right. So that's how variables work. We do this as human beings, right? When you got to remember somebody's phone number or something like that, what do? You jot it down on a piece of paper, you send a text, email to yourself, you write a text message to somebody, you put it in a note on your phone, whatever it is, you write it down somewhere so that you can refer to it later. That's variable storage. All right, that makes sense. Everybody can relate to in their real lives as a non-computer scientist person. They have to remember things and they have to store things somewhere and remember them later on. That's something we've all done. So how do we accomplish this in a programming language? So when you think about computer programming in general, when you first learn programming, you start with the basics, you learn a basic programming language, and you start learning some algorithms, searching, sorting, things like that. Then you start learning about some data structures. Okay, so when I say data structure, what is data structures? What does that mean to you for a programming language? So when I say data structures, what do you think I mean? Or give me a definition of data structures.
So basically like structuring the data into certain parts, which things to get categorized into with the other things, so that
Okay.
they have
Can you
a
give me some
certain
examples? Can you give me some examples of data structures you know of? Because there's some like traditional famous data structures. So the concept here is that a data structure is a structure for holding data. When we think about computer programs, we're usually manipulating data in some way and doing something with it. So it would, follow that there might be some structures that might help us hold data in, certain ways. The same thing exists in real life, right? If you have, all of you have socks, right? And all of you have, let's assume all of you have a suit of some kind, a dress or a suit, some kind of, larger garment, larger clothing. Now, at home, where do you store your socks? Maybe like in a drawer, something like that, drawer on a dresser. Okay. Do you put your suit or your dress in that same drawer? The answer is probably not, right? What do you do with dresses or suits? Hang them up, put them on a hanger, hang them up. So they're draped down. The structure in which you store a dress or store a suit is different than the structure that you store a pair of socks. Okay, because of the nature of your data. You have an expectation for a suit to not be wrinkly or a dress not be wrinkly. And because of that, because of the nature of that data, you need to store it inside of a certain kind of structure in order to maintain that data. Socks, you don't really care. You roll them up, you throw them into a drawer, and you hope for the best. All right, so we have much less concern with with socks when it comes to that. So, if we think about data structures in our traditional data structures, we might talk about an array being a data structure. We might talk about linked lists, stacks, queues, trees, graphs. So these are common data structures that exist. But now the idea here is that these are just the names of data structures. The fact that they have a name just means that they've become popular enough that people had to come up with some way of referring to it, right? Just like we talked about some of our structures built for holding clothing. Well, we have a thing called a dresser, which just has drawers in it. And what goes in those? Well, clothing that it makes sense to shove into drawers. And you maybe you have a wardrobe or a closet with hangers in it. So closet is the name of another data structure for storing clothes. And you put different kinds of things in the closet because the things you store in there are actually hung up to be stored in there. So we've given common names to these things. That doesn't mean that they're extra special as far as data structures go. Okay, we've just given a name to them. All right. So a data structure is any structure we've created to specifically hold data, and let's say for a reason. Okay, so here's some examples of ones that already exist, but in this case, I say we need a data structure to hold our name value pairs. So we need a data structure to hold our name value pairs inside of our for our programming language. Before I can create a language that knows how to store stuff, I need to have a facility for storing stuff. Okay, that makes sense? You can't go to the gas station and get a gallon of gas if you don't have anything to put the gallon of gas in. So you got to put it in either one of those gasoline fuel tank things, or you bring your car with you that already has the built-in fuel tank, whatever it is. But we have to have the structure for storing our data. So we need to invent a structure for holding our collection of name value pairs. All right. Now, if we talk about, so I'm going to refer to this as a variable environment.
I have a question.
Go ahead.
Okay, so talking about this thing, so do we have something like a data structure to hold a data structure in the background?
Well, the answer, I guess the answer is yes, because objects exist. So we can create objects in our languages, which we'll use to invent other data structures. But I think the real answer is it doesn't matter. I mean,
Okay.
my whole point on that slide is that data structure is this generic name that we give to an organizational method for working with stuff. Nobody says you have to store your socks in that drawer, right? In fact, I'm guessing several of us are pretty happy with just having our socks piled up in the corner of the room somewhere, right? We don't care. So there's no rule that says the only place that a sock can live is in that drawer. We've just decided that, oh, well, sometimes humans like to keep their, the world around them less messy. So they create these structures for storing stuff because it's convenient for them. Okay. These are concepts that we've carried out with, people who make, wood furniture and stuff like that in real life, or these are concepts that have been carried out with people who write software in the computer world. It makes it more convenient for working with things when you create structures for housing and manipulating that data. But that doesn't mean it has to be there. It just makes our life easier. So the more organized we tend to get, the closer to object-oriented programming we're probably dealing with. All right, so in this case, in this slide, I put out some examples of data structures that some of you should have heard of from your undergrad classes and data structures or programming classes, whatever it is. But understanding what are each of these things. An array holds a collection of like kinds of data all next to each other in contiguous memory. Linked lists are not necessarily next to each other in contiguous memory, so they're more memory efficient. Stacks support push, pop, and peek. So stacks work like a stack of magazines. That the last thing I add to it is on the top of the stack, which is also the first thing I take off of it. Okay, that's how stacks work. Queues are like a line. You go to McDonald's, you get in the queue. So it's first come, first serve. The first person who's in line is the first person who leaves the line. The last person who gets in line is the person who will get served last. Okay, trees. These are non-linear linked data structures. So this allows us to hold things that aren't necessarily linear in nature. Now we can have binary trees or n-ary trees or everything in between. Graphs, they loop back on themselves. So graphs are like a map, like a map of a state or something like that. All right, so these are just data structures that have been given names because we've used them to represent data commonly for problems in the past. Well, in our case here, since we are writing a programming language, which from a normal computer scientist, well, from a normal human's perspective, that's something that they would never do, right? But even from a computer scientist perspective, often we don't necessarily sit down and think about, well, maybe I want to write my own language. We're usually the wielder of languages, right? Like, why invent your own language when you already have Python or Java or C++ or pick your favorite language? Why write a new one? Well, that's a reasonable enough question. Sometimes that might make your life a little easier, especially with the interpreter example, because sometimes you'll want to write a language that just translates from one thing to another to make your life easier. And I'll give you a real life example. I know some of you were on Slack when I was doing this. This was last December. I was on a cruise. And one of the things I do, and my wife, I go away on vacation, is we go on a lot of cruises, and I like to sit at the bar and just write software. And I try to learn a new language, do something interesting. So I decided I was going to write a dice roller using a language called Chicken. And the Chicken language actually is kind of like how CPUs work, where every line of code in Chicken is the word chicken some number of times. So magic trick 1 might have just been chicken. Magic trick 2 might have been chicken, chicken. Magic trick 3 might have been chicken, 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 so on and so forth. But each of those magic tricks does a different thing. Well, so rather than me drive myself insane by writing the word, if I wanted to do one thing saying chicken, 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 and then the next thing I just said chicken, chicken, rather than doing that, I wrote an interpreter where I could feed it the command I actually wanted to get done in English, and it would give me the correct number of chickens for me to put into my code. So I created an interpreter that allowed me to stay sane Because the language only had like, I think like 30 different things it knew how to do. So it was like a CPU, like we talked about last time, that knew how to do 30 unique things. But rather than having to keep track of how many chickens I've written in a row for, number 26, I wrote an interpreter that just did the mapping for me. So I always got the correct number of chickens because I wrote an interpreter that converted between, the do magic trick 6 for me and the correct number of chickens, if that makes some sense. So writing interpreters is a skill that computer scientists could use somewhat commonly when they get into a career path that maybe has them doing similar things all the time, and they might want to build themselves a power tool to make their lives easier. Maybe you work in an industry where you kind of do the same thing all the time, and there's like this initial setup every single time. Maybe you get a new client or something like that, where it's like this tedious process, but you're always doing the same thing. And if you have the 4 or 5 pieces of information to get started, you could automate that process if you create a little interpreter for yourself. You feed it the 4 or 5 starting things, and it creates some kind of directory structure or something that has a whole bunch of starting files or whatever for whatever your job would normally be for getting the ball rolling with that company, whatever that is. So that's kind of the punchline as to the why. Now, if you get into compiled languages, now it takes that. Now you're looking at significantly more effort and probably significantly more buy-in. So compiled languages, you probably have some sort of vested interest in the underlying hardware. So you look at like C, C++. This was in the early days of computing, so we had a desire to tell the computer hardware what to do directly. Java, this was in a means of doing a little bit better than C++ was doing. C# was a Microsoft competition with the microsystems with Java. So these were built out of necessity, not necessarily, well, maybe business necessity and market leaders, as opposed to that we really needed it. Could we have survived without ever having Java? Probably. Sure, it brought some things to the table. We probably could have survived. It's not like C++ is terrible. We still use it today. Okay. But interpreted languages come out much more often. They make life more convenient for us when we wield them correctly. So the one thing I want to get across to all of you is that when we're in a class like this, the idea of writing an interpreter to make your job easier, more automated when you get into industry, is something you really might do. I mean, this is a real thing. So you want to be able to think about some of this stuff, because it's not that first thing that you sit down when you go to write a program, you say, oh, I'm going to write a new language. That means a whole bunch of different stuff. It sounds really complicated, but it's really not. It really depends on what you're trying to accomplish in the end. How complex does this language have to be? My interpreter for my chicken language thing was, I basically had 30 different instructions my interpreter understood. Each one gave me an output of some different number of the word chicken. chicken, or chicken, whatever, that kind of stuff. So kind of keeping in mind that these things are viable and valuable tools. So when we talk about a variable environment, maybe the first thing that should come to mind is like, oh, well, doesn't that sound like a dictionary? If you've worked with Python or something like that, where you have A is equal to 5, B is equal to 7, C is equal to 13, whatever. You're just a whole bunch of name value pairs. So when we're writing something like this in our language, we want to create a variable environment. So a variable environment, if we're going to put this in English, we're going to say this is a collection of name value pairs, where a name value pair is an object that holds a string for the name and a value for the value, where value is any type that our language currently supports. So this becomes kind of an interesting thing when we get started with our programming language. Artificially, so when we think about computer programming languages right now, we take for granted all the different types of values they can hold. They can hold numbers, they can hold characters, they can hold, well, integers, floating point numbers, characters, Boolean, strings. And then we can invent other kinds of types by writing our own objects. So really, we have a lot of power in our modern computing languages, but the reality is that we take that for granted. That a lot of that's given to us. So for our starting point, for our language, all we're going to be able to work with is numbers. We have a language of numbers right now. So every variable that ever will exist in our language will be a like a equals 7, or my age is equal to 21, that kind of thing. For right now, we only support numbers. Okay, so to do this in Java, we're going to need to have something that is going to be a name value pair. So I'm going to go ahead and create an object in Java. So this is in my interpreter. Create a new class. And I'm going to call this guy I'm going to actually call it name value pair. I like that. All right, so I'm going to call this guy a name value pair. And a name value pair is going to have a name. And for right now, I've said that the only kind of values we can hold are integers. So I'll actually store it as just an int for right now. We'll see the weakness of that next week or the week after. But for right now, name value pairs for integers is going to be good enough for us. All right, we'll go ahead and create our constructor for this guy. So he's going to take in a string name and an int value. All right, that'll be that guy. Now, these are both private, so we can't directly access them. So we want to give ourselves maybe some getters and maybe also a setter for the value, because we imagine that once we create a variable, we might, if I say a equals 15, in a little bit, I might want to change a to be a 6, for example. But I don't really need to change the name of the variable. So once the variable has gotten a name, I don't need to be able to change it. I do need to be able to read the name of it. But once it actually, but I might want to change the value of it at a later point in time. So I've made these private by default. So if you don't know what that means, go and look up public, private, protected for object-oriented languages. But this just means that these won't give us, you cannot access these fields outside of this class. So if I want to give access to this name outside of this class, I have to provide it. So I'll create a public function. We'll call this guy get name. This guy will return this dot name. So now I've given a public way for somebody to get the name from this private field. But they can't change the name. They can just get the name. Similarly, I'll go ahead and give them a getter and a setter. So we'll have a get value. That'll also get me the value, but I also want to be able to set the value, maybe a new value. All right, so this is my blueprint for my name value pair object. And my name value pair object allows me to build a single variable. So I'll just show you this as an example here. We'll go back out here. So now I can say I want a name value pair. V1 is equal to a new name value pair A7. B9. CSC549. Call this V1, V2, V3. All right, so now I can say something like system.out.println v1.getName. Actually, what I'm going to do here, well, I'll just do that real quick. So that'll show me its name is A. I can also say get value. Value is 7. All right, I'm going to teach name value pairs just for the sake of argument here, how to display themselves. So I'll say public void display system.out.println name. I'll maybe put a little equal sign and then this dot value. I'll teach name value pairs how to display themselves. So now in here, I can just ask each of these guys to display themselves. I can say v1 dot display, v2 dot display, v3 dot display, and it'll show me my 3 variables there. A equals 7, B equals 9, C equals 14. So just gives me a friendly way of displaying them. Now, after I display v3, I can say v3 dot set value to 23. And then I can say v3 dot display, and you'll see now it's changed to 23. Because I can update the value of a variable. Okay. We got here. All right, so I can update the value of a variable now. The issue here is that at this point, I've created an object called name value pair that knows how to hold a single name value pair. Now, when I talk about back here in our thing, a variable environment, this guy is a collection of name value pairs. So I need a whole bunch of those to add to my variable environment. So I'll go ahead and I'm going to create another object. And we're going to call this guy our variable environment. That's going to be the name of this object. And we're going to have variable environments hold a collection of name value pairs. And I'm going to choose to use an array list for my collection here. Doesn't really matter if you like using linked lists or something like that else instead. Array lists are pretty common because they do allow you to arbitrarily grow them in size. So I don't care which tool you use, but I'm going to give you the starting point of using an array list. So I'm going to go ahead and say private array list, but this is going to be an array list of name value pairs. And we're going to call this guy the pairs. Actually, let's call them the vars. That's really what it is. It's the variables. All right, so we'll call, I'm going to call it the variables. So I'm going to be more explicit. Okay, so I need to import java.util for this array list thing. All right, then I'll make my constructor here. So public variable environment. This guy's not going to require any inputs to get started. And what will he do? He'll set the variables equal to a new array list of name value pairs. So right now it's empty. All right. I'll go ahead and have a display method for this guy too. So public void display. We know that a variable environment is a collection of name value pairs. We know that each name value pair knows how to display itself right here. So for our variable environment, I'm going to go through all of my name value pairs and ask each one to display itself. Okay, I'll do this one as a for each loop in Java in case you haven't seen that syntax before. So I could do it as a for int I equals 0, I is less than, well, here, so we can say for int I is equal to 0, I is less than this dot, the variables dot size, I plus plus. And then I can say this dot, the variables dot get I dot display. So this gets the name value pair at bucket I and tells him to display himself. So that'll tell that guy to display himself. Alternatively, you can say for name value pair called MVP in this the variables MVP dot display. So these two things do the same thing. This is a for each loop that goes through every element of the variables. And each time through, I have inside of the variable MVP the next name value pair. I just tell that guy to display. Otherwise, I can use a traditional counter for loop that takes I on a voyage between 0 and the number of elements in the list in my collection -1. And then each time through, I'll just get one of those name value pairs and tell it to display itself. So you can choose which of those you like. I think we already have one of those in another place, so I'll just use this for each loop here for my variable environment. Now we have a variable environment and then we're dealing with a simple variable environment now. We're not going to be talking about scoping or anything when we'll be doing that soon, but right now we're just thinking about, okay, I want to have a place where I can store my name value pairs. Not when we say, like, for instance, if I go back here to driver and I have a string answer here in reverse, and I have a string answer here in main, this name value pair lives and dies with the variable scope associated with main. This name value pair, even though it has the same variable name, lives and dies with the scope of reverse. My entire program is governed by a single variable environment, right? So I have a variable environment that is, managing my entire running Java program. But at any point in time, when I go to use this variable here, answer, notice Eclipse is doing it for me. When I hover over this, notice it color coded this guy for me as orange, not this one up here, because a variable resolves to its most local definition. So when I'm referring to this variable answer here, it's going to find it in its most local place, which is up here. Okay, that means that in a real variable environment, we need to have scoping rules that allow us to determine what is the most local definition of a variable, not find me the first definition of a variable. So this initial memory environment we're going to be building here is going to be fairly weak, because if you have two variables in there, both called answer, whichever one was the one you put in most recently is the one you'll end up using. Okay, so don't worry about that right now. It's more like our thing won't work as well as it's ultimately going to work yet. Because right now we're just holding name value pairs, and we can probably just assume for the time being that all the names have to be unique. Because if they're not, we won't be able to guarantee we're getting the value we actually were asking for. And we'll talk about that next week when we get to it. So in my variable environment, I can display it. I need to be able to add a variable I need to be able to get value. All right, so this guy, this function, so this we're getting into what your homework assignment is going to be. So your homework assignment is going to be to write these pieces. So for add variable, this should take in a name and a value and create a name value pair and add it to the variables. This guy should take in a name and it should retrieve the value associated with that variable name. Now you can assume that any name you look for will be found. Okay, so I'm giving you a starting point here. So your homework is going to be for working with our system. I'm going to start off out here. I'm going to get rid of this reverse. I'm going to clean this up some since we aren't using these right now. I want you to be able to do something like this. Create a variable environment. And then be able to say env add variable A5, env add variable B7, something like that. Then be able to say system.out.println env.get value for A. Get value for B. And this should boil down to a 5. This should boil down to a 7. Okay. Eventually, what we'll look at next class is we'll put in a, so somebody you want to challenge yourself, I'm going to put in exception handling for what if you try to look for a variable named Z that doesn't exist. You know, I'll have it, you know, do something like a variable not found exception, something like that. But you don't have to do that for this. I'm going to assume that anything you're looking for will be in there. This is going to be our simple variable environment that we're working with. So this thing needs to be able to do two things. We've invented our own objects here. We have an object called name value pair, which holds name value pairs. We have an object called variable environment, which holds a collection of those name value pairs. When I first create a variable environment, it has 0 things in its collection. If I tell that guy to display itself, he'll go through and tell each guy to display himself. I'll show that to you here in a second. So if I say env.display, it'll do this. It's going to currently give me an error because inside of variable environment, this guy expects me to return an int. So for right now, I'll just return a -1, just so the error goes away, because I've advertised I'm going to return an int. So now what am I doing in my program? I'm creating an empty variable environment. I'm adding 2 variables to it. I'm going to ask it to display itself. Then I'm going to go ahead and get the value of A and B, which the way it's written right now is always -1, because I'm not actually searching. So you're going to need to search through your environment for those things. Okay, so there is my env. Oh, I also haven't written add variable yet. Yeah, so display is not going to show me anything. So this should show the should show all the variables in the environment. And that's already written. We've already written display. That's written. What isn't written correctly yet is your add variable, because it's not actually putting something in your collection. You're going to have to write that. All right. So for your homework, let me go ahead and commit this. And push it. All right, so now I already gave you this link, but I'll put it in the assignment anyways. If you want to use mine as a starting point for one of your assignments, what you do is you actually have to come up to mine. I can't do it in here because it's my own project, but you're going to want to fork it. So if I go to somebody else's project, let me go here and thought I can just go to home, gethome.com. Let's do I don't know, just search for Tetris or something like that. Yeah, here's a guy's Tetris project. Okay, so if I want to why can't I fork his project? Oh, I can't. All right, so if you went into my project here, you would see something like this. If you click fork, so I'll go ahead and click fork on this. And what it's going to do is I'll put it into, I'll put it into this guy. So what that does is it gives me my own copy of that repository. And that copy is mine to manipulate and do stuff with. But when I make changes to that, it won't change the original guy's repository, if that makes sense. So now I have my own version of that repository that I can make changes to. So if you want to use my code as a starting point, you're going to want to make sure that when you go to the page that I've given you, the GitHub thing, you fork that so you get a local copy on your you get a local copy on yours. So then what you can do is you can go here on yours and then you can say open with GitHub Desktop. When you do that, it'll go ahead and open GitHub Desktop. It'll see this is the thing you want to open that and ask you where do you want to put it on your computer, and you can click clone and it'll download it. And then you can open that project using Eclipse. So you would fork my project, then you would clone it to your computer using Git Desktop, and then you would be able to manipulate it and make changes. And when you made those changes and committed and pushed the changes, those changes will be made to your forked repository, not to mine. Because you won't be able to clone my repository and then update changes to mine because I own that repository. All right, so I'll go ahead and put this up here on Isn't this the right class? Is this not the right class? Oh, of course, it's not available. It's the other 549. So this will be homework number 2. Given this, implement, what did I name the 2 methods? Add variable and get value. Submit a link to your code on GitHub and the self-assessment template found on the left side of Blackboard. All right, so some of you are going to find this assignment very easy. Others of you may not find it very easy since there's all sorts of different backgrounds in programming here. You know, like I said before, though, as grad students, you should know how to learn. So, you know, this is a computer science program. The presumption is that one way or another, you either have some experience programming or you're going to figure it out. So, you know, I'm not going to help you with remedial programming problems. So you'll have to go and search for that stuff on your own or ask a classmate or something like that, because I'm assuming that one way or another you're showing up with the skills necessary to do this stuff. I'm giving you plenty of stuff to work with here as a starting point. This shouldn't take more than, if you know what you're doing, this assignment would take 5 minutes. So hopefully that then gives you some time to catch up on some other things if you are lost and need to go learn some other programming stuff, maybe through Code Academy or Code Wars or something like that. Okay, but I do have this self-assessment template that lets you tell me how long you spent on this and where you ran into problems in the event that you can't get it figured out or something. So I can give you some partial credit. So make sure you turn in both of those pieces. So I want to link to your GitHub repository where your solution is, as well as the self-assessment template where you can just paste that in here and answer the questions. That's over here on the left-hand side. You can click it and read what that looks like. And this is going to be due on Monday by 10 a.m. $100 points. All right, and like I said, I don't care if you work in groups on this and things like that, but just remember that the expectation is that you're learning while you're doing the homework, because I'm going to find out on the exam that's worth 40% of your grade whether or not you know how to do this stuff or not. All right. So questions, comments, concerns, bribes.
Oh, we can try out the new code so that we can have some little practice.
What do you want to do?
I mean, with a new code, I mean, the one which you gave, instead of that, can we try it on our own?
Yeah, you can try whatever you want on your own.
Okay, sure.
And I am wondering that last time I have submitted the Hello World program. I'm wondering if I can know if I did right or not in the GitHub.
Well, I'll be grading them today.
Yeah, grading. I'm not asking for grading. I'm just did I do in public? Just kind of I forget. Can you access mine or not?
Well,
Just that's what. If
a
you
link
can
to
give
it
in
in
Slack, that will be good.
Put a link to it in chat right now to your repository.
Okay, just give me a minute. I will. This one.
Oh, you put it in Slack or did you put it in chat?
Sorry, I put in Slack. Sorry.
Oh, in 549. Oh, there you go. All right. So you should be able to do this yourself. Click on it.
Yes, I ran. I did. I feel that's good.
Yeah,
Things are
looks good
okay.
to me. That looks fine to
Okay.
me.
Thank you. Okay.
All right. I will see everybody on Monday.
See ya.
Thank